All right, so let's begin. It looks like our first question is 10 from the review. So let me bring up my OneNote and then I'll start sharing. All right, perfect. So number 10 on the review. And if there's any questions while I'm working, feel free to just stop me or correct me if I make any mistakes, or you can always send a chat and I'll see it. Okay, so this one says find all zeros of the following polynomial function. So we're given f of x equals x cubed minus 8x squared plus 25x minus 26. So for starters, a good question to ask yourself is, how many zeros does this have? You're told to find all of them, so it would be great to start off knowing how many you need to find. So first of all, the degree of this polynomial is 3. And that's because my exponent on my leading term is a 3. So that means that I have a degree of 3, which means I also have 3 zeros. So I'm just going to write that down. So degree 3 means that we have 3 zeros. Just something helpful to know. So one of the first ways that you want to start out by doing this is to use that rational roots theorem. So this helps us know which ones, or like which possible rational numbers could be roots of this polynomial. So that's a good thing to start out with, is listing those out. That way you know really what you're working with here, and then you can try plugging some in. So if you need a refresher, this is the theorem where we take factors of p and factors, or sorry, not factors of p. P is equal to the factors of 26 in our case, and then q would be equal to the factors of 1, because there's a 1 in front here. So if you don't remember that, we'll go through this process. So let's go ahead and start by identifying what p is. So p is going to be equal to plus or minus all of the factors of negative 26, 26, either one's fine. So our factors are going to be 1, 2, 13, and 26. Our next step is to go ahead and figure out what q is. And q is going to be all the factors of 1, since we have a 1 in front of our x cubed. So q is equal to plus or minus just 1. Oh, sorry. I didn't mean to write negative 1. There we go. So our next step is to do p over q, and then p over q gives us all of our possible rational roots, hence the name the rational roots theorem. So p over q is equal to plus or minus, and you do all of the things in p over each thing in q. So I take every single thing in p and put it over everything in q. So since there's only one thing in q, this makes it really easy, because I'm just doing 1 over 1, 2 over 1, 13 over 1, 26 over 1. So because there's only one thing in q and the thing in q is a 1, it's pretty easy to do. So this is just 1, 2, 13, and 26. So now I've identified all of my possible roots for this polynomial, or all of my rational roots, I guess. So this is going to help me to go through some of these, plug them in, and see if any of them work. So just a reminder, if you're not remembering this process, we pick some of the ones from our possible ones, we try plugging them into the polynomial, and if we get an answer of 0 when we plug that in, that means we've successfully found a 0. So that's what we're going for here. We're going for plugging some of these in into the polynomial, and if we get a 0 back out, that means we've got one. So that's your goal. Because that would take time for me to go through and plug all of these in, I won't do that right now during the study session. I already know that it's 2, just a hint, but you could go through and plug some of these in, and you would end up seeing that 2 works. So let's just plug 2 in just to check that it does in fact give us 0. So f of 2 is equal to 2 cubed minus 8 times 2 squared plus 25 times 2 minus 26. And this gives me 8 minus 32 plus 50 minus 26. Then if you go through and do the math here, you get negative 24 plus 24 equals 0, which is exactly what we're looking for. So we've got a winner, 2 works. So don't forget what we're doing. Don't lose sight of the goal here. The goal is to find all of the possible zeros, and you've just found 1. Cool, 1 down, 2 to go. So your next step now, you might be wondering, what am I supposed to do now that I found this 1 0? Like, that's great, but I still have 2 more to find. So once you find 1 0, we can take and factor our polynomial down. That way we can find the other 2. Because just by looking at this polynomial, I don't think you guys necessarily want to sit here and try plugging in more of these ones. And not to mention, we could have complex roots, which you're never going to find by plugging in rational roots. So once you find one of your rational roots, we're going to go ahead and factor our polynomial, and that way it's easier to identify the rest of them. So to factor, you could do polynomial division or you could do synthetic division. I'm going to do synthetic division because I prefer it and I think it's a little faster. So we're going to do synthetic division with our 0 that we just found. So I'm going to put my 2 up here. And now I'm going to write the coefficients of each of my terms in the original polynomial. So I have 1, negative 8, 25, and negative 26. So this process of doing synthetic division right here, don't lose sight of what you're doing. You're taking your original polynomial and you're dividing it by the factor x minus 2. And that's because we just found that 2 is a root. It's a 0. So that's what we're doing right here. We're taking our original, dividing it by the factor that we just found, and that's going to give us what's left, and then we can solve that piece that we get. So to do synthetic division, we bring this 1 down, multiply 1 by 2, that gives me 2. Negative 8 plus 2 is negative 6. Negative 6 times 2 is negative 12. 25 minus 12 is 13. And 13 times 2 is 26. And then negative 26 plus 26 is 0, which you should get. So a little mental check, if you've found a factor, you've found a 0, and you're now doing the division, you should never get a remainder. You should always get 0. And that's because when you divide a polynomial by one of its factors, there should not be a remainder there. So if you're getting a remainder, something's off and you should go back and check your work. Not necessarily that your factor's wrong, maybe you just did your division wrong. So if you do not get 0, stop, go back. So the cool thing here now is that these numbers right here form the coefficients on my polynomial now that I've gotten after the division. So now I have x squared minus 6x plus 13. Sweet. So this is nice because you guys know the quadratic formula, and this is a quadratic. So we can use the quadratic formula here to solve for the remaining zeros. So the goal is to do that division so that we get a quadratic that we can now solve using something we already know. So you guys know how to use the quadratic formula, so let's do that. So I won't take too much time filling this out, but 6 plus or minus 36, I'm going to need a bigger square root. Minus 4 times 1 times 13 over 2. And that is equal to 6 plus or minus negative 16 over 2. So I'll slow down a little bit here because we have that square root of negative 16. And if you guys remember, this is where we bring in the I. That way we can actually evaluate this. So this gives us 6 plus or minus 4i over 2. I'm going to divide my 6 and my 4 by 2 and get 3 plus or minus 2i, which is great because now we found the remaining zeros. So your zeros are 2, 3 plus 2i, and 3 minus 2i. Oop. And now we're done. And that's it for this one. Check yourself. After you find your zeros and you're writing them down, make sure the number of zeros that you have down is the same as the degree of the polynomial. So I listed 3 zeros. My degree was 3. I'm good to go. Are there any questions or clarifications needed on this one before I move on to the next problem? Okay. So let me check the Jamboard and see what our next one's going to be. All right, looks like our next one is 6. So So let's jump into 6. Okay. So 6 is not too terrible. It might be a little tricky and you might just not, might just not know where to start here. So 6 says solve the following equation for x, show all steps leading to your solution. So we have 5 to the x plus 3 power equals 1 over 5. So you can already see that we're trying to solve for x, and the x that we're trying to solve for is an exponent. It's in an exponent here. This is an exponential equation here, and we want to solve for x. So there's a little theorem that you guys have used in class and have heard about, that if you have the same base here, and we've got like that x plus 3 is an exponent, we can set their exponents equal to each other. So if we have the same base, then we can set the exponents equal and solve for x. So your goal is to write 1/5 as 5 to some power. So I'm going to say that again. Your goal is to write 1/5 as 5 to some power. And I think this kind of trips students up because a lot of the times it'll be a negative power, and that kind of is a little tricky and not something that we usually do a lot. But let's remember that 1/5 is the same as 5 to the negative 1. And I'm just going to cover why that's true. So 5 to the negative 1 power. Remember when we have a negative exponent, that means that we put it in the denominator of a fraction and that exponent becomes positive. So this becomes 1 over 5 to the first, which is just equal to 1/5. So if you're struggling on these when there's fractions, definitely refresh your memory on when you've got negative exponents and what that means, because when you've got a fraction over here and we want to write it with a base of 5, we're going to need a negative exponent. So you might have to go back and look at those like algebra rules that you learned a while ago. But this is nice because now we have 5 to the x plus 3 power is equal to 5 to the negative 1. And the great thing about this is since their bases are the same, we can set the exponents equal. So now we've got x plus 3 equals negative 1. And that's because we have two things with the same base that are equal to each other. If they have the same base and they're equal, that also means their exponents need to be equal. I can't tell you 5 squared is equal to 5 cubed. That doesn't make any sense. It would need to be like 5 squared is equal to 5 squared. You notice their exponents have to be the same if their bases are the same. So now I just subtract 3 and I get x equals negative 4, and that's all. And if you want to check your answer, go ahead and plug in negative 4 for x. You plug in negative 4 for x, you'll get 5 to the negative 1 power, and you'll see that is definitely equal to 1/5. This is a very, very, very good problem to know how to do. Something of this nature. Just the concept of writing things with the same base and then understanding that then their exponents have to be equal. Okay, any questions on this one before I move on? All right, cool. So people want to see some of the questions on number 7. So let's do 7. These aren't really that long, so I don't have a problem doing all 3. So let's just do all 3 of them together. So A is h of g of x. So I think students struggle with these a little bit, but when you say them out loud, it kind of makes a little more sense. So when you see A, read it as h of g of x. So when you see that little O in the middle, that just means of. So h of g of x. So kind of a weird concept, but what that means is we're going to take our function h, and h is equal to x minus 1 over 2. So we're going to take h, and everywhere we see an x, we're going to plug in what g of x is. So I'll say that again. So everywhere in h that we see an x, you're going to plug in all of g of x, that whole function. So when you say it out loud, h of g of x, it really means take the function h and evaluate it at the function g of x. So let's just do that really quick. So h of x is equal to x minus 1 over 2. So first, identify everywhere I see an X. So I'm just going to highlight here because I have an X right in front. And everywhere that I see an X, I'm just going to take and plug in my whole g of X. That's it. So now I plug that in and I get X, the square root of X minus 3 minus 1 over 2. And that is it. So let's try doing this for B. So now I have h of f of x. So let's do the same process again. So this is saying that we want to know what h evaluated at f of x is. So that means I'm going to take h, and everywhere I see an x, I'm going to plug in f of x, the whole thing. So let's write down h of x again is x minus 1 over 2. Let's point out every spot that has an x, which is just that first spot again. And I'm going to fill that in with my whole function f of x. So all that means is I now plug that in and I get x plus 1 minus 1 over 2. And that simplifies down to just x over 2. And that's it. So let's do the same concept now on C, except let's use an actual number. So this is h of g of 7. So there's a bit of a difference here. It's not an x now, it's actually a 7. But that means there's just like one little extra step that we can do. So we want to evaluate h at whatever g of 7 is. But we can actually figure out what g of 7 is. So let's do that. So g of 7 is equal to square root of 7 minus 3. All I did was plug 7 into my function g, and that's because here I have g evaluated at 7. This gives me the square root of 4, which is equal to 2. Awesome. But don't forget that you had h of g of 7. So now I know that g of 7 is 2. So it's basically like now you could just plug in 2 where g of 7 was. So now it's kind of like you're saying h of 2, which is really just h evaluated at 2. So let's do that. So h of 2 is equal to 2 minus 1 over 2, which is just equal to 1/2. So that is your final answer. It's kind of like you're working backwards almost. So it's like you kind of have to start on the inside and work your way out. So you first start off by doing g of 7 because it's on the inside, and then you work your way out and do h of whatever g of 7 was. I have an activity later if we have enough time to get around to doing it. That's on composite functions, so that might be helpful. But does this make sense for now to everyone? Or do you have any questions? All right, cool. So now we've done all 7. So my next one is 1f. So let's go ahead and do that one. All right, good. 1f. So this kind of goes hand in hand with one of the other ones we did. So I'm glad someone asked this. If a third degree polynomial, stop right there. Third degree. What does that tell you? Third degree. This means that we have 3 zeros. Good. Mental note. If a third degree polynomial has a real 0 at x equals 2 and a complex 0 at x equals 3 minus 5i, where is the other 0? Okay, so we've got 2 of them. We're just missing 1. So we have a real 0 at x equals 2, and then we have a complex 0 at x equals 3 minus 5i. So this is where you have to remember your complex conjugate theorem. And this says that whenever we have a complex number that happens to be a 0 of a polynomial, its conjugate is also a 0. So think of complex numbers as coming in pairs when it comes to zeros. So if you have one of them as a 0, you have its other partner also as a 0. They're just called conjugates of each other. So you can't have just one complex 0. You can't. You have to automatically have 2. So you can't just have 1. You have to have 2. You can't just have 3. You'd have to have 4. So they come in even numbers because they come in pairs. So wherever you have 1, you have its partner, and they're called conjugates. So there should be just bells going off when you see this one complex 0, and you should be There's a second. It's its conjugate. Just be aware of that. Burn that into your brain because that's really going to help you. So if 3 minus 5i is a 0, its conjugate is also a 0. So let's remind ourselves what a conjugate is. A conjugate is just switching that sign that comes between the real number and the imaginary part. So if 3 minus 5i is a 0, that means that 3 plus 5i is also a 0. So I just switch the sign that's between my real number and my imaginary number. That's it. Or you can think of it as I switch the sign that's in front of the I. And that's all. That's your answer. All right, does anyone have any questions on that? Okay. Let's see. So we have 11b and 12b. Okay. Let's see what these are, because I don't remember. Okay. Wait, what's 12b? Oh, 12b is like the same concept. Okay. So I'm thinking this person just wanted to focus on asymptotes. So yeah, let's just do that then. Okay. All right. So first of all, let's remember how we find vertical and horizontal asymptotes. So, so you know what? Let me start with 11. Sorry, not 12. Okay, here we go. On 11. So we want to find the asymptotes here. First of all, we're going to do the vertical ones. So vertical ones are pretty straightforward. The vertical ones, you just want to identify any values where the denominator is equal to 0. That's it. So this one isn't too bad. So let's see. If we want anywhere where the denominator is equal to 0, all we have to do, and I'm just going to write off to the side here, we just have to identify anywhere where x minus 1 is equal to 0. That's all. So to solve this, move the 1 over, and then you just get x equals 1. And that's it. So vertical asymptote at x equals 1. Something, I guess, to refresh your memory is that when you're doing the vertical asymptotes, don't forget to write your rational function in the lowest terms. Do not forget that because sometimes, and I think we'll see that on the next one, you will have factors that cancel out. And if you don't write it in the lowest terms, you might assume that there's a vertical asymptote that actually isn't one. If we're able to cancel factors out, that's actually just called a hole in the graph. So make sure that you write it in lowest terms before doing vertical ones, because you might accidentally identify too many vertical asymptotes that actually aren't really asymptotes. It might just be a hole. So make sure your rational function's in lowest terms. This one is already in lowest terms. Nothing can be canceled out here. But on the next one, I think we'll see that we have to write it in the lowest terms. So just a helpful reminder. Remember then that doing the horizontal ones, that refers to the degree of the numerator versus the degree of the denominator. So we need to identify the degree of the numerator and the degree of the denominator. So first of all, I can see that my degree of my numerator here is 2. And then I can see that the degree of my denominator is 4. So now you need to kind of compare these in your mind and think which one has the higher degree, the numerator or the denominator. In our case, it's the denominator, because like I said, denominator has a degree of 4, numerator has a degree of 2. So when the denominator has a larger degree, that means that we have a horizontal asymptote at y equals 0. So perfect. And these are just things that you should, I hate to say it, but have memorized for the horizontal ones, because the horizontal ones just comes down to comparing the degrees. If they're equal, there's a different thing you do. If the denominator is bigger, there's a thing you do. And if the denominator is less, then there's another thing that you do. So there's really not like a whole lot of computation here, not like with the vertical ones. It's more just like knowing what means what. Sorry, unfortunately, that's not the most fun thing to tell you, but that's probably the best way to go about this. The other thing to know is that we do not have any oblique asymptotes. And that comes into play when there's, I believe, a difference of 1 between the degree of the numerator and the denominator, but we already identified that our denominator is a degree 4 and the numerator is 2, so that's not the case here. So just note that there are none. Okay, so that's it for that one, for the asymptotes. So I'll go ahead and let me make sure no one asked to see the whole problem. So give me 1 second. Okay, someone asked to see all of 12. So we will just do all of 12, which is good. 12 is a good one to look at because 12 you actually, oh no, wait, 12 you don't factor. There's one on here that you factor. I don't know what one I'm thinking then. Okay, whatever. Sorry to disappoint. But let's just go ahead and do 12. So 12 is a rational function. It's r of x equals x plus 1 times x minus 5 over x squared plus 1. So first step, part A, is to write the intercepts as ordered pairs. So let's remember what an x-intercept is. An x-intercept happens when y is equal to 0. So the x-intercept happens when the output of the function is 0. The nice thing about rational functions and their outputs is that if you want an output of 0, you're only concerned with the numerator. Because as long as our numerator has 0, we don't care what the denominator is because it doesn't make a difference. There's no difference between 0 over 8, 0 over 7, 0 over 10 million. They're all 0. So you only care about where the numerator is 0. So we want to look at that for our x-intercepts. So let's identify where x plus 1 is 0. And that happens where x is equal to -1. So that's one of them, -1, 0. And let's do where x minus 5 is equal to 0. And that's at x equals 5. So we know we have another one at 5, 0. Okay. Our y-intercept is slightly different. The y-intercept is wherever x is equal to 0. So not too bad, you're just going to plug in 0 everywhere there's an x. So you're just going to evaluate the function at 0. So r of 0 is equal to 0 plus 1 times 0 minus 5 over 0 squared plus 1. This just ends up being 1 times -5 over 1, which just gives us -5. So that means we have a y-intercept at 0, -5. Now we're good with that one. Okay, so let's do B. This is doing the asymptotes again. So let's do the vertical ones first. The vertical ones are where our denominator is equal to 0. So let's go ahead and identify that. So we have x squared plus 1 equals 0. Well, this is x squared equals -1. And I don't know about you guys, but this is definitely complex. And when we're graphing things and when we're doing points, we're not concerned about complex things. If I told you to graph the point 3 plus 5i, where would you put that? Like, you have no clue how to graph that. You can't, it's imaginary. So like if I told you to graph 0 and then 3 plus 5i, where does that go? So the only solutions to this would be complex, and we're not concerned about those when we're doing asymptotes. The only times that we're talking about complex is when we're talking about zeros, and that doesn't help us graph it. We're just wondering what zeros of a polynomial are. So in this case, we're not worried about this. This actually just means that we don't have any, because we can't plug anything in to x squared plus 1 that'll give us 0. That's a real number. So none. So sorry, I'm going to erase this because I wrote on part C. So then let's look at the horizontal ones. So this is where we have to compare our degrees again. So the degree of my numerator is 2, and the degree of my denominator is 2. So when I have the same degree in my numerator and my denominator, it means that I just read off the coefficient on my leading terms. So What that means is we just need to know what the leading terms are in the numerator and the denominator. So if I have r of x equals x plus 1, x minus 5 over x squared plus 1, you can't see the leading term of the numerator right now, and that's because it's in factor form. So you can go ahead and FOIL these out. You don't have to FOIL it completely. You just have to FOIL it so that you get the first term. So all that would be doing and FOILing would be, but you can do it completely. It doesn't matter. I'm just trying to save you time. So all that would be is doing x times x, which just gives you x squared. That's all you need to know. You just need to know what your leading term would be. If you wanted to finish the FOILing out, that's totally fine. But I just need to know what my leading term would be in my numerator, because that's all I'm concerned about when I do the horizontal asymptotes, if their degrees are the same. Because all I care about is x squared over x squared, and then I just want to read off their coefficients. So if I read this off, that gives me 1 over 1, which is just equal to 1. So I have a horizontal asymptote at y equals 1. Sometimes you might be given a rational function where the numerator is not factored and you can just read it right off. Easy, totally fine. But if it's in factor form, just remember that you need to know what that leading term is, if your degrees are the same of the numerator and the denominator. Like I said, there are 3 different cases for the horizontal asymptotes, so really review those, know those, and just know how to go about each of them depending on what you're given. So once again, we don't have any here, which is nice. So let's go ahead and look at C. So C says, are there any holes in the graph? So when I talked about holes briefly, I said that a hole occurs when you have something that you can cancel out. So if I factor my rational function and then I can cancel factors out, I have a hole at wherever that factor is equal to 0. And that just means that our function isn't defined there. And I know in recitation, I briefly showed like Desmos, and I was like, hey, look, there's a hole at 3. If you go exactly to 3, it says undefined. Try it. Try graphing something on Desmos that has a hole. You'll see it. So that just means that our function's undefined there, but we couldn't cross anything out. This was actually already in the lowest term, so we don't have any holes. So if you don't cross anything out when you're writing your rational function in lowest terms, there are none. Okay. Sorry. Okay, that's everything for number 12. Are there any questions on 12?
Yeah, for the x-intercepts, do you only deal with the numerator then?
Yeah, so just to cover that really quickly, recap. So for the x-intercepts with the rational functions, you just want to know where the output of the function is 0. So we just want to know, so let me write this down here. We want to know where 0 is equal to x plus 1, x minus 5 over x squared plus 1. So we want to know where that's equal to 0. But the cool thing is with a rational function, we only care about where the numerator is 0 because it doesn't matter where the denominator is 0. It doesn't matter what the denominator is, more importantly. So like if I gave you like 0 over 7, that's just 0. If I gave you 0 over 1,000, that's just 0. So it doesn't matter what the denominator is because 0 over anything is 0. I mean, unless you have 0 over 0, but we're not going there. So 0 over anything is just going to give you 0. So you only care about where the numerator is equal to 0.
Okay, thank you.
Mm-hmm. Okay. Let's see. Oh, sorry, guys. I'm yawning over here. Let's do number 3. I don't even know what 3 is. Let's see. Okay, this is a really good application of a few things we've talked about. So form a polynomial with real coefficients that has degree 5 and zeros at x equals 2, x equals negative I, and x equals 1 plus I. First of all, you know that you have 5 zeros because it says it's degree 5. You better have 5 zeros if it is degree 5. Oh, say this again. The number of zeros and the degree of your polynomial better be the same. This is like a very important concept that continues to show up in like multiple things that you guys talk about. So we know we need 5 zeros. we have x equals 2, which is one of them, x equals negative I, which is another, and x equals 1 plus I. But like I mentioned earlier, if you see a complex zero, I swear, you just better look at it and go, there's a conjugate of it. So like, I don't know, whatever you have to do to train yourself to see that zero and say, there's another one missing. Its conjugate is missing. Its conjugate is also a zero. There should just be like red flags going up. So if you see negative I as a zero, you should also realize that I has to be a zero. So where there's a complex zero, its conjugate is also a zero. They come in pairs. So since we have negative I as a zero, we also know its conjugate is 1, which is just I. Boom, there's another one of our zeros. Since we know 1 plus I is a 0, its conjugate is also a 0, which is 1 minus I. Boom, another 0. Now we've got all 5. So step 1, identify all 5 zeros. This is like, I swear this is a trick that's thrown on like multiple questions of like, what's the other 0? Or like, let's see, number 4, what's the product of 3 minus 2I and its conjugate? Conjugates are very important and they show up a lot. So know what a conjugate is. Understand that where you have one complex 0, its conjugate is also a 0. That's a big takeaway. So let's go ahead and write this polynomial. So we know that wherever there's a 0, there's a factor that corresponds to that 0. Oh my gosh, I'm so sorry guys. I think I need some coffee or something. Woo, okay. So wherever there's a 0, there's a factor that corresponds to that 0. And that factor always is x minus that 0, no matter what. So wherever you have a 0, your factor is x minus that. So we have a 0 at x equals 2. So first of all, let me call my polynomial f of x, just to start us off. So we have x equals 2. So our factor is going to be x minus 2. Done. Next one. We have a 0 at x minus I. So our factor is x minus negative I. And that just gives me x plus I. We also have a 0 at I. So I have x minus I. And this one is usually what throws students off, is like the 1 plus I, the 1 minus I. That whole thing is a 0. So when you do the factor, just do x minus the whole thing 1 plus I. Make sure you have those parentheses. If you don't have them, it's not correct. You need to subtract the whole 0. Don't just throw the subtraction in there without the parentheses on that 0. Make sure you have them. And then we have to do our last one, which is x minus 1 minus I. So because our 0 is a little different and it's like 1 plus I, 1 minus I, it's a complex number. It's not just, one thing. It's not just 2. It's the addition of 2 things. You need to make sure that when you subtract it, you put parentheses around it. Okay, does everyone get number 3? This is a really good problem. It's a good one because it addresses that wherever you have a 0, you have a factor. The degree needs to be equal to the number of zeros, and then complex zeros and their conjugates. So that's a really good one. Okay. Next we need to do 16. 16, that might be like the last one. I'm not sure. Oh, we don't have to do 16. Super sorry if you're in my class tomorrow. You actually don't need to know how to do 16. See, I crossed it out here. It's because I did not realize this said take-home technology question. There is obviously no take-home technology portion of your exam for either of my classes. Like last time there was a technology portion, but this time there isn't, so you do not need to know how to do 16. You can forget about it. Okay. I have done all the questions that people have posted on the Jamboard. Are there more questions? Like, I'm down to do whatever you guys want me to do on the study guide. Like, anything I'm down for. $17. All right. Someone would like to see 17. Let's do it. Okay. Ooh, this is a good one. Let's do this one. You guys are going to see my graphing skills. Actually, you all already know my graphing skills are not skills. So, okay. Ooh, yeah, this is a very good one. There's a lot of concepts tied in here. There's literally 1, 2, like 3, 4, 5, 6 concepts in this question. Great question here. So this is going to use a lot of the stuff we've already talked about, but now we're just going to combine it. Okay, so first of all, very similar to one we did earlier, where it was also a cubic. It was something to the third power. And we talked about how we needed to find the possible rational zeros, and then we found a rational zero, and then we factored it. So we're going to start off with the same type of like process that we did before. So this is a cubic function. We're going to go ahead and find one of the zeros so that we can factor it and do that whole process again. So back to the rational roots theorem. So we're doing the PQ and the P over Q. Are you seeing a pattern here? Because like they definitely follow a pattern. So P is my factors of 12. So P is plus or minus 1, 2, 3, 4, 6, and 12. Yes, we have a little bit more here than last time, but that's okay. Q is my factors of 2. So this is kind of a good example. We use something a little different where there's more than just one factor of Q. So a little exciting here. So Q is plus or minus 1 and 2. All right, next we're doing P over Q. So we take each thing in P and put it over each thing in Q. So this one's a good example, like I already said, because there's more than just one element in Q. Last time we just had 1 in Q, and so it was kind of like boring, you're just putting everything over 1. This one's a little more exciting. So P over Q is plus or minus, and I'm just going to go through taking each element of P, putting it over each thing in Q. So I'm starting with 1 in P, and so I have 1 over 1. And then I'm going to do it over my next thing in Q, which is 1 over 2. And now I'll move to my next thing in P. So I'm doing 2. So I do 2 over 1, and then 2 over 2. And then I do it with 3, 4, 6, and 12. Some of them may be repeats. So I'm writing them in fraction form just to take that extra step so you guys see what I'm doing. But we'll simplify this down because like obviously 1 over 1 is just 1. So we'll write it a little nicer after. So 3 over 1, 3 over 2, 4 over 1, 4 over 2, 6 over 1, 6 over 2, 12 over 1, 12 over 2. Okay, so let's simplify this down. So 1 over 1 is just 1. 1/2 is 1/2. 2 over 1 is 2. But 2 over 2 is just 1, and we already have 1, so we don't need to write it again. 3 over 1 is 3. 3 over 2, we need that one. 4 over 1 is 4. 4 halves, 4 over 2 is just 2, and we already have 2, so we don't need to write it again. 6 over 1 is 6. 6 over 2 is 3, and we already have 3. 12 over 1 is 12, and 12 over 2 is 6, and we already have 6. So it looks a little nicer once we simplify this down. So let's go ahead and start plugging some numbers in. Like I said, I'm not going to waste your time and go through and plug them in because I know that you guys are capable of doing the algebra. So I know that the answer is 2. So I'm going to plug in 2 and check it and just make sure this works. So let's do f of 2. So this is 2 times 2 cubed minus 5 times 2 squared minus 4 times 2 plus 12. All right, so 2 times 8 minus 5 times 4 minus, 4 times 2 is just 8 plus 12. 16 minus 20 minus 8 plus 12. So this equals 0, which is good. So like I said, you're going to plug in these possible rational roots that you have, and then you're just going to check to find one that equals 0. So we found one that equals 0. We're good to go. So now we found one of our zeros, which means we also have a factor. So we're going to do synthetic division. You can do polynomial division. I like synthetic division better. I think it's a little nicer looking, but whatever you want to do is fine. So now we're going to take and divide our polynomial by this factor that we just found. So that ends up being 2 up here. And then my coefficients of my polynomial are 2, -5, -4, and 12. And so the first thing you do in synthetic division is bring down the 2. 2 times 2 is 4. Sorry, that's a terrible 2. -5 plus 4 is -1. -1 times 2 is -2. -4 minus 2 is -6. And then this is -12, and that's 0. I'm going to emphasize this again. If you have found a 0 and you do synthetic division by that 0 and you do not get 0 at the end, I swear I could not have said 0 more times in that sentence. But if you do not get a 0 at the end, something is wrong. You should not have a remainder. So that number that you get at the end here, that's whatever your remainder is. You shouldn't have a remainder. If you found a 0 and you've done the synthetic division correctly, you should only end up with something that gives you 0 at the end. So a side note, because I saw a lot of this in both classes, I saw like in this type of a problem where I said, hey, find, or the first step was to find a 0. So most people were able to go ahead and do the rational roots theorem. They did P, they did Q, and they did P over Q. Everything was good there. But then the issue came in to where they started plugging the numbers in. I found a lot of people in my classes started doing synthetic division with each of them. Like they would do synthetic division at 1, and then if they didn't get 0 at the end, they said, oh, that doesn't work. That's true. That is totally true, that if you do synthetic division with a true 0, you should get 0. So that method isn't wrong. It's just not quick. I can't imagine doing synthetic division 3-4 times to check if something's a 0. I would rather just plug that number into my polynomial and see that I got 0 out. If that makes more sense for you and that's easier to do synthetic division, totally fine. You can do synthetic division a million times. It's okay. I just think it takes longer, and I don't want to mislead you guys into thinking that you need to do synthetic division to check up here if something's a 0. You can just plug that number in to check. But it's up to you. I just saw it a lot, and I was like, ooh, do people think they need to do synthetic division? So I'm not sure. Answer this question. Okay, so someone asked me if we only need to find one real 0. So because we have a cubic here, something to the 3rd power, we're finding 1 0. So that way we can factor it into a quadratic because we know what to do with a quadratic. We know to use the quadratic formula. So yes, for this polynomial right here, you only need to find 1 0. And we just need to find 1 to get it into a quadratic. So just 1. So we're good here. And remember that when you do synthetic division, these numbers that you get are now the coefficients on your new polynomial. So we have 2x squared minus x minus 6. All right, and so this is nice because, let's see. Okay, yeah. Sorry, I was trying to remember what I was even doing in the problem. Okay, we're graphing this. So we're trying to factor it so we can identify the behavior at those factors. So let's write this in factor form now. So factored form, we know already that we have f of x is equal to, and we already found a 0, x minus 2, which is great. But let's go ahead and now factor this new thing that we found. So I'm going to do the x method. This is like my favorite. -12, -1, -4, and 3. I'm doing the factoring quickly because I don't want to waste time with factoring. I assume you guys can do the factoring. Cool, so then this gives me 2x plus 3 times x minus 2. Awesome. Okay, great. So I'm going to pause here and explain something really quick. If you remember doing the worksheet with me in recitation, bounce, wiggle, cross, if you remember doing that where we looked at a polynomial and we looked at each of its factors and we said, oh, what's the multiplicity? That tells us if this bounce, wiggles, or crosses. That's what we're doing here. So our goal was to find a zero. That way we could factor the polynomial. So it's the same like beginning initial process as when you find zeros. You're just finding all the zeros is what I mean. But instead you find 1 0, that way we get a quadratic, and that way we can factor the quadratic down because we know how to factor a quadratic quickly. You guys know how to do that with like the little diamond method, the X method, whatever you guys do. So our goal was to take this polynomial, get it into factored form. That way we can look at its behavior. When you think of graphing a polynomial, think of the bounce, wiggle, cross. Think of, the end behavior. There's a few things that you guys probably remember doing. I know this was a little bit ago. This was probably closer to your last exam when we started doing these things. So polynomials, when you're graphing them, think bounce, wiggle, cross, end behavior, and intercepts. Those are some things that you need to graph them. Okay. Note that here I have 2 of my x minus 2 factors. Very interesting. This just means our polynomial is x minus 2 squared times 2x plus 3, because I have 2 of them. All right, let's take each 0, because a 0 is also an x-intercept, and let's identify the behavior there. So I have a 0. I'm going to make a little chart. I have the multiplicity that I need to know, and then I need to know if it bounce, wiggles, or crosses. All right, so my zeros are 2, and then my 0 of this other term right here, the 2x plus 3, that's a 0 of x equals negative 3/2. All right, cool. So my multiplicity of my 0 of 2 is 2, because I have a squared on that factor. The multiplicity of negative 3/2 is just 1. And then you guys got to dig way back and remember, a multiplicity of 2 means that you bounce. Something even means that it bounces off the x-axis. And a multiplicity of 1 means that it crosses. Okay. After we finish this problem, I'll write like a little checklist of things that you guys should find when you're graphing a polynomial. That might help too. So once I finish this, I'll kind of like sum it all up in like a little list. Maybe that'll help. Because I know after a while, all this stuff starts to look the same. And after a while, you're like, what even is this? So now that I have my behavior at those x-intercepts, I'm going to talk about the end behavior, because now you know what this graph does at the x-axis, but you want to know, what do the ends of it do? So like, what do the ends of my polynomial do? So think back. So when we talked about the fact that end behavior is just equal to the leading term in your polynomial. So the ends of my polynomial behave like 2x cubed. And I just got that from up here because my leading term is 2x cubed. That is helpful because when you think about something that's a cubic, you know that it does this at the ends. And this is just something that you should know. You should probably memorize this. There's like a chart in the book and stuff, but when you have something that's cubed, its ends behave like that. And that's because if you've seen a cubic, it looks something like that. And you notice its ends, one goes up and one goes down. So if your leading term has an odd exponent, it has this kind of an end behavior. And if it has an even exponent, they both go up. But ours is odd. Okay, one last thing, everyone. So next thing we're going to look at is what our y-intercept is. And our y-intercept is just where x is 0. So if we plug in 0 for all the x's, so f of 0 gives me just 12. So my y-intercept is at 0, 12. Okay, I'm going to recap the things that we found before we graph them, and that way maybe it gives you guys like a little step-by-step process or like a checklist. So graphing a polynomial. This is a polynomial, not a rational function. So two different things. So with graphing a polynomial, you want to know the x-intercepts. And then on top of that, you want to know if they bounce, wiggle, or cross at the x-intercepts. So sometimes to find the x-intercepts in this, you'll need to factor. The next thing you want is the end behavior. And the last thing that you want is your y-intercept. So this is like a little summary of the things that you need. So we want the x-intercepts. And to find the x-intercepts, factor it. It is much easier to read your x-intercepts off when you just have something factored. And then we know those rules in our heads of, okay, if it's got a multiplicity of this, it bounces, wiggles, or crosses. So find the x-intercept, identify if they bounce, wiggle, or cross, and then do the end behavior and then your y-intercepts. This is all you need to give a rough sketch. So now let's do it. Okay. Okay, so let's see. And I know that we have a y-intercept of 12, so I'm just going to do 12 up here that way. We have something. So let's go ahead and graph these. So we know we have x-intercepts at 2 because we have a 0 of 2. So I'm going to graph that point. This is 2, 0. I know I have another one at -3/2, which is about right here. And that one is -3/2, 0. I know I have a y-intercept at 0, 12. So that's right there. Now our next step is just to go ahead and put all these things together. So we know that at 2, my graph bounces. So we know that it comes down, hits the x-axis, and then bounces back up. So the nice thing is that we also have our end behavior, which we know that the right end of my graph faces up. So that kind of helps because I know that this end of my graph is going to be facing upwards. So I'll draw that in. And because I know that my other end, because of the end behavior, is going to be facing downwards, I'll just draw those things in. That's just the direction that my arrows are going to go. This might help because you know that it bounces at 2. So I have an idea that it comes down and then bounces off the x-axis. And I know it has to come through the 12 because I have a y-intercept. Next, I know at -3/2 that it has to just cross. So that's not too bad because it has to come down here, it has to cross, and I know what my end behavior is, and that's that. So I would say when you go to graph them, put on your intercepts, roughly write what your end behavior is, and then you can just use the behavior at the x-axis to kind of fill in the rest of the graph. That's all we're concerned about here. So to graph a polynomial, know its x-intercepts, if it bounces, wiggles, or crosses, the end behavior, and then the y-intercept. I know if you guys graph things on Desmos, like you might get very weird polynomials that like shoot straight up and then come straight down or something. Do not worry about that. This is not a test to use Desmos on. No one is concerned about how like precise the thing, like no one's going to care if you, I mean, there's no way for you to know off the top of your head that this polynomial, like let's say you get one on an exam, there's no way that you need to know that that polynomial happens to shoot up, come back down. Like there's just like things that are weird in polynomials. That's not what anyone's asking you to do. They're asking you to just give a rough sketch. So do not panic and don't feel like you need to use Desmos and that your graph has to be perfect to get like a good grade on this question. You just need to use these concepts to give a rough sketch. Like, let's say this isn't what the graph looks like, and let's say like it actually goes up like, I don't know, it does something weird in between them. That's okay. That's not what you were asked to do. You were asked to use x-intercepts, y-intercepts, and behavior and bounce, wiggle, cross to graph it. Yours does not need to be like 100% exactly how the one on Desmos looks. Just a tip. Because you are doing a rough sketch. Okay, let me look at the Jamboard and see if there's any more questions. No, it doesn't look like it. Does anyone have any questions about anything I just did off the top of their heads?
I just have a question on the next one after that for 18. Do you just use synthetic division for that, where you just like use 2 and then do synthetic division and then like use the remainder?
Yeah, so you totally can. You could do synthetic division by 2, and then, like you said, you would need to get a remainder of 0 if it was a factor. Something else that you can do too is literally just plug 2 in. And if you plug 2 into that polynomial and you get 0, then it's also a factor. So there's kind of 2 options. You could do synthetic division, hope you get a remainder of 0, or you could just plug 2 straight in and hope you get 0.
Okay, thanks.
Can you show how you factored it for number 17 again?
Yeah, like, do you want where I factored, let me see, hopefully you can see my mouse. Do you want where I factored it down here, or do you want like the whole thing from here down?
No, from the 2x squared minus x minus 6.
Got it. Yeah,
Yeah.
I can do that. Let me see, I think there was a chat, so 1 second. Okay, so we'll be going over 1H after I talk about this factoring, but we will do that. Okay, so let's take a quick break and discuss factoring really quick. So I know that I need to factor 2x squared minus x minus 6. I'm going to come over here so that you guys see. I'm writing in teal now. So I need to factor this. My favorite method is the diamond method or the X method, whatever the heck you want to call it. I learned this, I don't even know, probably like 8 years ago. So this is my favorite method. So I take, and in my X, up top, you want to put negative 6 times 2, which is negative 12. And down below, you put negative 1. And that's just because I have negative 6 times 2, which is negative 12. And then here I have a negative 1. Okay. So I filled out my X, and this means that I'm looking for two numbers that multiply to be negative 12, but that add to be negative 1. So let's think. We need 2 things that multiply to be negative 12 and add to be negative 1. Well, that's going to be negative 4 and 3. You can check me on that, and that works. Normally, when you do the X method, you're able to do this really great thing, and you're able to just do, okay, X minus 4 times X plus 3, and I'm done. That does not work in this case. Be on the lookout, because that only works if this number right here, the one I'm highlighting in purple, that only works if that is a 1. If that number is a 1, great. You can just take this straight from the X, diamond, whatever, and write X minus 4, X plus 3, and you're all good to go. If that thing is a 2 in front, that does not work. So that is a little red flag, and that's why I had to do it slightly differently. You'll notice this doesn't work. Let's FOIL this. This is not going to give you what you want. X squared minus 4x plus 3x minus 12. That gives me x squared minus x. Did I do that right? Yeah, minus 12. Yeah, that is not what we started with. We started with 2x squared minus x minus 6. Does not work. Okay, scratch that. Now that I've done a little detour and showed you why that does not work. So I guess I would say when there's a 1 in front, that's a little shortcut that you do. But the reason that that shortcut works is because behind the scenes, you should really be doing this. So let me show you. So we take and write 2x squared. That is this first term right here. And now we write minus 4x, because I'm taking a negative 4 from here, plus 3x, taking my 3 from here, minus 6. So all we do is take this chunk right here, and it's kind of like we replaced negative x with it. So all you did was replace negative x with negative 4x plus 3x, and if you do the math, negative 4x plus 3x is still negative x. So we haven't changed anything. We just used the numbers that our diamond little method or X method gave us to go ahead and change negative x to negative 4x and negative 3x. Okay, now this is a method that I know you guys talked about. It's a little different, but now what you do in your mind is group these two things together. So now I want to see what I can pull out of my first group. So what do these two terms have in common? So these two terms both have in common a 2x. And if I pull that out here, I just get x minus 2. And you'll see why I'm doing this, because I'm going to do it on the next one now. So here, oh wait, I wrote, I'm sorry, this should be plus 3x. I don't know what happened there. So on the next one, I'm going to see what I can pull out of 3x minus 6. And I can pull out a 3. And this gives me x minus 2. All right, cool. Now you should stop here and make sure that these things in the centers here, these parentheses, what you have inside those parentheses should be the same. That's how you know you've done this correctly. Because now I'm going to take 2x plus 3 and then x minus 2. And that is my factor form. So yes, it is very annoying when there is a 2 in front of the x squared and not a 1, because you have to do this like whole detour and like break this thing down and do like, I don't even know, this other like 3-step process. But this is the way to do it. And if you FOIL these out, you will get the right thing. Where if you try to do it, you know, and just write them straight from the x, you won't get the correct thing. So side note, if there is a 2 or something else in front of your x squared term, you need to go ahead and do this method and like break it down. Okay, so that was a little factor. Oh, sorry, that was a little factoring detour. Let's talk about 1h. I got a request for that one. Okay. Oh, I like this one. This is a very good question. So this is given f of x equals 2x over 7x minus 1, what is the range of f inverse of x? So I'm going to take a quick detour here and explain this, because this is a really, really, really good concept to know. You've noticed I've really emphasized a few concepts here. You should trust me. So let's talk about what our function f does. So our function f takes our range and it goes to the domain. I'm just drawing a picture for a visual. So our function f of x takes the range and goes to the domain. There's a pretty little picture. Now our function f inverse of x, the word inverse, in this case kind of just means it does like the opposite. It kind of is backwards of what f of x does. So if we have the same picture, f inverse of x actually now goes from, oh wait, what did I write? I wrote these backwards. Oh my gosh, guys. I'm really, okay, hold on. Okay, now we're on track. My goodness. Okay. Okay, let me repeat myself. F of x, my little function in teal up here, takes my domain and goes to my range, just like a normal function, domain to range. F inverse does the opposite and goes from the range to the domain. That is very, very, very important that you know that. So f of x goes from the domain to the range, and f inverse of x goes from the range to the domain. So it just goes backwards. You could also think of f inverse of x of just being here and just going from the range to the domain. That's probably like a little bit of a better diagram to think about. So let's just draw it in one. So f of x is in teal there, and it takes you from the domain to the range, and f inverse of x takes you from the range to the domain. So it just goes backwards. Okay, now let's use that here. So given this function f of x equals 2x over 7x minus 1, what is the range of f inverse of x? So if you look at my little diagram over here that I drew, this is very helpful, and it tells you that the range of f inverse of x, so all of the outputs of f inverse of x, it's actually just the domain of f of x. So my domain of f of x is my range of f inverse, and my range of f of x is my domain of x inverse. They're just swapped. So I know that a lot of students here on H would look at this and be like, okay, let me find the inverse first, and then let me find the range of the inverse. Let me just make this a lot easier for you. Instead of finding the range of the inverse, just find the domain of the actual function, because you know that the domain of f of x is the range of f inverse of x. That is a really important concept to know, and I'm so sorry because I literally like accidentally said it backwards when I first started. Just try and erase that from your mind, and what I just said is correct. I think we're all a little tired here. I feel like that's the takeaway. So I'm gonna say this again. When you want the range of the inverse, you can also just use the domain of the original function. Yes, if you went through the process and found the inverse and then found the range, yes, that would be the same thing, but why do that? Let's just make less work for you and it'll be quicker. So in a test setting, this is a little faster and it's less work. 10 out of 10. So let's go ahead and find the domain here. So the domain of f of x is just all the things that we can plug in here. So do we have any restrictions? Well, we don't want our denominator to be 0. That is always a big red flag when you have rational functions. You don't want a denominator to be 0. So let's identify where we don't want that to be 0. And that happens to be at x equals 1/7, which means that we don't want to plug in 1/7. So that is the only thing excluded from our domain. So the domain of f of x is -infinity to 1/7 union 1/7 to positive infinity. Or you could say x such that x is not equal to 1/7. Either way is fine. But that's really great because the domain of f of x is the range of f inverse of x. So we know that the range of f inverse of x is in fact the same as the domain of f of x. And that's your answer. So that was a little side note to really, emphasize that point there, to understand that when you do the inverse, the domain and the range flip. Okay, so I have a question about domain and range. So yeah, domain is the x value and range is the y value. I would think of it like, I think a good way to conceptually think about this, is that the domain is your inputs and the range is your outputs. So the domain is anything you plug in and the range is everything you get out. So if we look at this little graph I drew here, this little like figure, whatever, the teal function, which is f of x, goes from the domain to the range. So its input here, all of the inputs are the domain and all of the outputs are in the range. But the inverse takes everything from the range of f of x and actually just takes it to the domain. So it goes backwards. So maybe in this case, it's easier to think of it as input versus output. I don't know if that helps. So like all the inputs of f of x are also all the outputs of the inverse. But yeah, in a sense, the domain is always the x values and the range is always the y values. Yeah. Okay, are there any other questions? We only have 10 minutes left. I was going to do an activity with Jamboard on composite functions, but there's only 7 people, so there's really no point in putting you guys in breakout rooms. And we did do some practice with composite functions, so I'm okay not doing it. But are there any other questions? If there's no other questions, I will stop sharing my screen. And you guys are totally free to go if there's no other questions. So So I guess with that being said, good luck with your studying. And if there's anything else that you need, feel free to send me an email or a text in the meantime. And I hope you guys all do amazing on your exams.
Thank you.